Dr. D. Sangeeta is currently a senior lecturer at the Department of Chemistry, Anna University, Chennai. She has completed her PhD in the field of polymer chemistry from the University of Madras in the year 2000 and has teaching and research experience of more than 10 years. Her research interests are in the following fields: fuel cells for clean energy, functional membranes for desalination, and polymers for biomedical applications. She has published more than 20 research articles in national and international journals and has more than 40 research articles in national and international proceedings. Presently, she is guiding 6 research scholars for their doctoral degree.
Welcome to the UGC lecture series on the topic of solar energy, part 4. In the series of topics on for solar energy, in the earlier episodes, we have talked about the various uses and importance of making use of the solar energy. We have also spent time on seeing how this solar energy is extracted for our various utilizations, especially by 2 different methods, namely the thermal conversion and the photovoltaic conversion. We also dealt with certain examples, that is, so what is a solar collector, how it is utilized in transferring the energy from the solar to our various uses, and then we looked upon the working principle of a solar plant, and we also dealt with the advantages and the disadvantages with the solar plant as our various utilizations. Then we moved on to what is called the second type of most important type of conversion, solar energy conversion, that is the photo conversion. Here in this photo conversion, there is a component, a very important component, a vital component called solar cell, otherwise called as photovoltaic cell. This particular cell is utilized in this conversion process to convert the solar energy directly into electrical energy. A little bit of introduction about this solar cells we have seen in the previous parts, and today let us focus more on the details of the principle, working mechanism, operation that are associated with the working of the solar cell. Let us move on to the construction and then the working mechanism. Initially, the construction about photovoltaic cell. It is a solar cell that is typically consisting of 2 thin layers. You have a layer called upper layer and a bottom layer called lower layer. Essentially, the upper layer is short of 1 electron in the outer orbital of the atoms that are present in the upper layer, whereas in the lower layer, the atoms which are present here has 1 unpaired electron in excess in the outer orbital, or the valence electron is available as 1 unpaired excess electron present in these atoms that are available to undergo excitation. These electrons which are available in the outermost orbit of the atoms that are present in the lower layer can be easily excited to go into the upper layer. So, the upper layer is deficient of 1 electron and the lower layer has got 1 electron excess per atom. Hence, when a potential energy is going to fall on this lower layer, the unpaired electron has the capacity to get transferred from the lower layer to the upper layer. This is the basic happening that is happening in your solar cell. Hence, a solar cell is essentially consisting of an upper layer and a lower layer, where there is a movement of electron that is going to take place from the lower to the upper layer at appropriate condition. Now, let us move on to the working. How does the photovoltaic cell work? Kinetic energy that is gained from the collision of photons of the sunlight can eject the electrons from the lower layer immediately into the upper layer. That means, the kinetic energy that are possessed by the photo energy that is coming from the solar, that is coming from the sunlight, they, when they fall on the lower layer, they have the capacity to eject out or excite the electrons that are present in the outermost layer of the atoms that are available in the lower layer. Hence, when these electrons they capture the energy, the kinetic energy that is available in the solar radiation which is falling on it, they get excited and can have the potential to get shifted into the upper layer, which has got a higher energy level. This charge movement creates a potential difference. This movement of charge from the lower layer to the upper layer creates a potential difference between the two layers, and thus enables the current to flow through the external circuit. When the electron is able to jump from one layer to the other layer, the electrons are available in the conduction layer very freely, which are available to move freely, which is nothing but the flow of charges or flow of electron, and this is nothing but the current that is generated in the system. Hence, the electrons that are available at the top layer is available to move around in an external circuit. For example, if a motor or an electric device is going to be connected in the external circuit, then the electron starts moving through the circuit. Hence, the connection between the two layers are available for the movement of electron from the lower layer to the outer layer, and when you are going to have an external circuit, the electrons flow through the external circuit and come back to the lower layer once again. So, that is the basic working of a photovoltaic cell. Photovoltaic cells are made out from the semiconductors. The most commonly used semiconductors would include silicon and germanium. There are other materials too which are being used for the same purposes. Now, let us focus on the type of photovoltaic cell that is made out from the semiconducting materials. A conventional silicon based photovoltaic cell consists of a top layer and the bottom layer. The top layer is going to consist of an ultra thin layer of phosphorus doped silicon. This is called N-type silicon because I need to have one electron lesser in the system. So, it is an ultra thin layer of phosphorus doped silicon which is called the N-type, which is consisting of a polycrystalline silicon wafer that is going to be placed on the top of the P-type silicon. So, the top layer consists of all these constituents, whereas the bottom layer of the system can consist of boron doped silicon, which is the P-type. So, you have the N-type conducting material at the top layer and you have the P-type silicon available in the bottom layer to do their functions. A very basic structure of a silicon based photovoltaic cell may consist of the following features or layers. The first layer is called the cover glass, which is a transparent cover at the top to protect the whole cell, and you have an anti-reflecting layer just below the cover glass. This anti-reflecting layer consists of a coating of silicon nitride or titanium dioxide. This is available in order to increase the amount of sunlight that can be transmitted through the device, that is your photovoltaic device. So, such an anti-reflecting layer is a must, is required in order to focus the large amount of sunlight that is going to be transmitted into your photovoltaic cell. Then comes the third layer of contact grid. This contact grid is essentially a metallic grid because you need to maintain the conductivity through a metallic conductor because the electron flows through the metal conductor. Hence, you need to have a contact grid here to catch hold of your electrons. Hence, the contact grid is made out of a metallic grid. This is required in order to serve the purpose of electrical contact and to allow the sunlight to fall on the semiconductor. So, this layer plays a dual role. One is to connect the electrons to have the connectivity for the electronic conduction. At the same time, it is going to allow the sunlight to easily fall onto the bottom layer where the excitation is going to take place for the electrons available in those atoms present in the lower layer. Then comes the N-type silicon layer, then the P-type silicon. Their functions have been already explained in the previous slide. They have one excess electron and one less electron in the top layer, and this P-type silicon is going to give the electron which is going to get excited and get shifted to the top layer, that is your N-type silicon layer. And the P-type silicon layer is nothing but available along with the N-type to make a junction called P-N junction. The junction between the P-type and the N-type silicon is called a P-N junction, which is formed between the two layers of P-type and n-type silicon layers. Then finally, once again you have a back contact, and this contact is also a must in order to continue to have the electronic conduction or end the movement of electron from the top layer in the external circuit and ends up over here. So, the back contact is also made out of a metallic layer in order to maintain the electrical contact. Hence, the whole structure of silicon PV cell consists of a cover glass, an outer transparent glass cover, then comes the anti-reflecting layer to concentrate and focus the sunlight for the transmission into the device, and then you have a contact grid, then you have the n-type silicon and p-type silicon. The junction between them is called p-n junction, and finally at the bottom you have another metallic contact called the back contact. This is required in order to maintain the flow of electrons from the top layer to the bottom layer in an external circuit where you can make use of a device to get operated. The semiconductors are being used in a number of semiconductor devices. Such a construction of photovoltaic cell based on semiconductors are being used for various applications, various electronic devices. In solar cells, the semiconductor is doped to produce two different regions that are separated by a junction called p-n junction, and across this p-n junction two types of charge carriers, namely the electrons and the holes, cross. The electrons are nothing but the negatively charged carrier which jumps from the bottom layer to the top layer. Once the electron is going to jump into the excited level or the higher energy level, it leaves back a condition called hole. So, this hole is positively charged, hence the movement of electron in one direction and the holes in the opposite direction is always happening in the p-n junction, which is the constituent of the whole PV cell setup. This transfer or migration, it is called as, of charge from one region to another region results in a difference in the potential value. It results in what is called the potential gradient, and it is this potential gradient that is responsible, that is happening between the two layers, is the one which is responsible or enables the flow of current to take place. In a very simplified operation of a photovoltaic cell, otherwise called as a solar cell, the sunlight is allowed to fall on the p-n junction diode. The absorption of photons from the light leads to the generation of electron hole pair. As many electrons as it is getting shifted, so many holes will also be simultaneously formed. So, you can always call them as electron hole pairs. So, the absorption of photonic energy from the light, it actually leads to the generation or production of electron hole pairs. The electrons are drifted or moved towards the upper layer called the n-type layer, while the holes are drifted towards the lower layer or the p-type layer or p-type end. Hence, both the electrons and holes move in the opposite direction. Now, when the two ends are connected through a conductor, a conducting medium in an external circuit, the current, electric current is allowed to flow through. The movement of electron is nothing but the flow of current. A typical silicon solar cell can produce about 0.5 to 0.6 volts direct current under open circuit condition. This is called OCV or OCP condition, that is under no load condition. That means when the current is not being drawn, the maximum potential that is arrived or achieved could be equal to 0.5 to 0.6 volts in a small silicon based solar cell. The current or the power output will depend on the following factors. The one important factor is the efficiency of the PV cell itself, how efficiently the PV or the photovoltaic cell works, its size or the surface area onto which the fall of sunlight is going to take place, and also the intensity of the sunlight that is going to strike on the surface of the cell. So, the three important factors that decides the amount of current or the power that is going to be generated by the photovoltaic cell are: Number 1, the efficiency or the performance of the photovoltaic cell. Number 2, the surface area or the size of the photovoltaic cell. And number 3, the quantity, the intensity, the amount of sunlight that is going to strike on the surface of the cell. All the 3 factors decides the amount of current that is going to be produced by the photovoltaic cell. After the during the operation, after the electrons and holes have drifted towards the upper layer, that is n type end, and the lower layer, that is p type end respectively, that is when the electrons and holes have diffused across the junction, p-n junction, the region is now called as depletion region, because already the electrons are drifted and your holes are also drifted. Now the junction, you call it as depletion junction or depletion region. It is called the depletion region because the region now is not going to contain any mobile charge carriers. Once they are drifted, it is called depletion region, and such a depletion region can also be called as space charge region. Now, when the two ends are connected in an external circuit, the electrons that are going to be created in the n type side travel through the wire and can power the load and continue through the wire till it is going to reach the p type side on the other end. On reaching the p type side, it is once again going to recombine with a hole in the p type side. So, this is the normal functioning of the electron and hole movement that is happening in the photovoltaic setup. Let us have a short break and then continue with the details of the operations. Welcome back after the short break. Now, having seen the basic principle of working and the construction of a solar cell, we will move on to the material that is used as a photovoltaic material, example the silicon itself, their advantages and limitations. Silicon as a PV material, its advantages are silicon wafers can be made into very thin layers, which is very useful in construction of the PV cells. They are available in larger size, bigger sizes, where you can increase the surface area. It is also cheaper. It is also found abundantly. Basically, sand is the source for your silicon. Its natural forms are silica and silicates that are naturally available, from which the silicon can be produced. And most importantly, the other important advantage is it is non-toxic. In general, it is non-toxic. It is not going to cause any harms to you. But we have to remember, the silicon dust, if it is available in a very fine particle size, has little adverse effects on our lungs, which may lead to silicosis, a disease called silicosis. This is about the direct conversion into electricity by making use of a photovoltaic cell. Now, this picture explains the layers, your n type layer, your p type layer, an external load is available here. The electrons move through the external load and then comes and joins with the hole over here. This is the direction of your electron flow. All this happens due to the fall of your light energy onto your system. Hence, to have once again the explanation of how it is working, photovoltaic cells are capable of directly converting the sunlight into electricity. A simple wafer of silicon with wires that are attached to the layers are available. Current is produced based on the types of silicon that is used for the construction, that is your n type and the p type, that are being used for making the layers, and each cell can produce about 0.5 volts. The battery is always needed in order to store your energy, and there is going to be no moving parts as far as this photovoltaic cell is concerned. Hence, there are no wear outs, but because they are exposed to the weather, their lifespan can be lesser. For example, it can be almost about 20 years. Later, we have to think whether we have to change the solar cells, panels and arrays in order to gain back the actual performance of the photovoltaic cell. Now, how about the crystalline silicon when it is going to be used as a material for making your photovoltaic cell? Crystalline silicon can be available in various forms. It is available as monocrystalline silicon. This is very costly, but it is very efficient. It is also available as multi or polycrystalline silicon forms. This is of course less in cost, but the efficiency is also lesser. The other third form of silicon is ribbon silicon. Thin films of multicrystalline silicon structure is basically called the ribbon silicon. Its production cost is of course lower, but again the efficiency is also lower. These are the different forms of crystalline silicon. Silicon atom. What is so special about this silicon atom, which is making it to be very useful in the construction of the photovoltaic cell? A little bit information about the atomic level of the silicon atom. Silicon atom basically contains 14 electrons that are available in 3 different shells. The first 2 shells are completely filled, whereas the outermost shell, the third shell, is consisting of half filled, that is 4 electrons. Hence, you have totally 14 electrons, and it can share 4 electrons with 4 neighboring silicon atoms in order to complete its octet. To have a stable structure, to complete its octet, the 4 electrons that are available in the outermost shell of the silicon is readily available to share or is readily available to share with the neighboring electrons, neighboring atoms, with 1 electron on all the 4 sides, so that it can complete its octet. Hence, this becomes a very crystalline structure, because it can bond in all the 4 directions for 1 electrons each, so that it can bond with 4 electrons, and already 4 electrons are available in the outer shell, and hence it becomes 8 electrons and a complete octet. This leads to what is called the crystalline silicon. Hence, the basic atomic structure is the one which is facilitating the silicon to be available as the silicon crystalline silicon, and hence their usages are found to be very useful in the photovoltaic cell applications. The crystalline silicon in its purest form is a poor conductor of electricity. Unless it is doped, it does not become a p-type or n-type conductor. It is a pure insulator. It does not conduct electricity at all in its pure form, but an impure silicon is only useful in the solar cell. Silicon is doped with phosphorus, which is a 5 valence electron atom, to form the n-type silicon, so that you have 1 excess electron in the system, and the silicon is also doped with boron to form the bottom layer, which has got 3 valence electron, which forms the p-type silicon, where you have 1 electron lesser. Let us move on to the classifications of solar cells. If we look into the history, how these solar cells have developed over a period of time, they can be classified into different generations: first generation, second and third generations of solar cell developments. The generation actually indicates the order of which each type of solar cells were developed and how did they become important in terms of cost, efficiency, operation, everything we can discuss, and hence there is a difference between each generation that have been developed over a period of time in our history. First generation solar cells. Such cells which are developed in the first generation solar cell type consist of large areas, number 1. They have high quality and single junction devices. So, they are termed as the first generation solar cells. Of course, they are costly also. The example for a first generation solar cell is the single junction silicon device. Achievable efficiency here in such silicon device is only up to 25%. The cost of production and technology, they are very costly, and this is due to the involvement of high energy and also the labor inputs that are required to prevent any further progress in the cost reduction. It was very difficult. Although it was functioning well and the achievable efficiency was 25%, the cost involved in the technology and the manufacturing and production of your solar cell is very high. Then came the second generation solar cells. In such cells, they were developed in order to reduce the production cost and the energy that are required for the manufacture of the silicon based solar cells that were done in the first generation materials. Alternate materials were developed during this second generation period. For example, cadmium telluride, copper indium gallium selenide, shortly called as CECUGC, and amorphous silicon, or the various alternate materials that were tried for functioning as a photovoltaic cell. Such materials that are used in the second generation solar cells were applied in a thin film onto a supporting substrate like glass or ceramics in order to reduce the basic cost of the cell. Alternate manufacturing methods were also developed during this period. For example, vapor deposition methods like CVD and PVD, chemical vapor deposition and physical vapor deposition, and electroplating methods were also developed in order to manufacture such alternate materials. Although the cost of production was reduced during this period, the efficiency were also reduced due to their low quality processing methods. Then came the third generation solar cells. Such third generation solar cells are being developed right now in order to enhance the performance and also to simultaneously reduce the cost of production. Now the aim is not only to improve the performance, efficiency to be increased, but also an effective cost reduction methodology are also being tried presently in the third generation. The aim of the third generation technologies is to achieve an electrical efficiency as high as 30 to 60%. Enhanced efficiency were based on multi-junction PV cells, modifications of the incident spectrum, use of UV light for thermal generations, and so on have been tried in such enhanced efficient systems. Specific technologies are also due to silicon nanostructures, thermoelectric cells, and so on. Now, as a summary, in this particular part 4 of solar energy, we have gone into the details of construction and working of a photovoltaic cell. What are the different layers, the functions of the different layers in forming your photovoltaic cell have been seen in detail. Then we moved on to specifically the silicon based PV cells, its basic structure, the operating mechanisms were discussed, and the advantages of using silicon as the photovoltaic material for the construction of the photovoltaic cell were discussed in detail. Then the specific advantages and the different forms of crystalline silicon were seen, how they are advantageous in forming your photovoltaic cell, and finally we touched upon the classification of solar cells based on their development, that is based on their generation, first, second and third generation. And right now we are existing in the third generation. There is a concentration towards two different things. One is how to improve the efficiency of the existing photovoltaic cell. Research activities are going on in improving the efficiency, as well as the second part, most important part, is the cost effectiveness of the photovoltaic cell. How do we bring down the cost effectively to have a good performance as well, are being done in the third generation solar cells. Here are few questions. Explain the construction and working of a PV cell. What is crystalline silicon? Explain the operations of a silicon based photovoltaic cell. What are the advantages of silicon as a photovoltaic material? How are solar cells classified? Thank you.